Okay, now that we've learned a little bit about the electromyogram signal, where it comes from and some of the challenges associated with recording it, let's talk about the design of an amplifier you're going to build, or at least the key components of that design. So the first part of your amplifier is of course going to be your input stage, which is the part that's going to be connected directly to the skin. And this is going to be your instrumentation amplifier. Again, we're choosing an instrumentation amplifier for two main reasons. One, it has a very high common mode rejection ratio, so the noise associated with the EMG signal will be able to be suppressed because that noise is common to both inputs, noise due to issues such as electromagnetic interference from the power in the room that you'll be working. The other main reason for having an instrumentation amplifier, of course, is its very high input impedance because the impedance of the skin can be very high. The other thing to note with the instrumentation amplifier is we need to provide it with some sort of a reference. Although we're making a differential measurement, we're going to output a signal that's referenced common to some ground. And in order to have a relatively small common mode signal, we're going to choose our reference to be the body. So you'll typically attach the two electrodes that go into the positive and the negative terminals of your instrumentation amplifier over the muscle of interest. And then you're going to attach your reference electrode to another point on the body that's not over a muscle. Typically we put it over a bony landmark such as your elbow or maybe your wrist, and that provides a nice common reference for your system. So that's our first component. The second component of your system now is going to be a high-pass filter. And you've already learned about many different ways to build high-pass filters, and it's up to you to choose one that you think is most appropriate for your design. The purpose of the high-pass filter is to reject low-frequency noise. And again, a common problem with biopotential recordings, such as the electromyogram, is that you can have a lot of motion artifact due to movement of the electrode on the skin. And that motion artifact typically occurs on the order of 10 hertz and below. So you're going to want a high-pass filter that's capable of rejecting that noise. One other thing we know about biopotential recordings and electromyograms is that they're very small. They're on the order of microvolts to maybe millivolts, so we need to amplify them. So we're going to have some form of gain in our system. And the very last thing we need to worry about is a low-pass filter. And this low-pass filter serves a couple of different purposes. First of all, we want to concentrate our amplifier on the frequencies that are of interest to us. And we'll talk about that a little bit more in the next card. But so this will reduce any high-frequency noise that we might have. And it also serves another purpose that you've learned about recently, and that's as an anti-aliasing filter. Ultimately, we're going to amplify our signal so that you can record it through the new scope. The new scope works by sampling your signal at a set rate, and you want to make sure that you eliminate any components of your signal that are above the Nyquist frequency so that you can prevent aliasing. And your low-pass filter will also serve in that role. So again, these are the key components of your design. There's one thing in many commercial amplifiers that I haven't talked about because you won't be building it, but that's some way to isolate the patient from the mains power supply. So if you were working in industry and building an amplifier to be attached to a person, and that amplifier needed to be plugged into the wall to supply its power, you need to have something called an isolation transformer or an isolation amplifier between the power supply and the patient. But as we've already talked about, and I want to emphasize again, your circuit will only be run by the battery, so there should never be any chance of connecting you to the power supply to keep things safe. So you don't need to worry about isolation in your design, but I just want you to be aware that in a commercial system that would always be present. So now for each of these components, there are many ways that you can implement them. You've learned about many ways to design amplifiers, many ways to design filters, and it's up to you to decide how to implement them in your biopotential amplifier. Good luck.